Alright, so hi everyone. So now let's look at these examples. So these examples we stop it in our tutorial session. So we have tried to find the electric field from the plane, okay? The plane x equals to 2 and y equals to 3. But we haven't tried to look at the electric field for the line, right? So you have a line x equals to 0, z equals to 2, and the line charge density is 10 pi nanocoulomb per meter. So you have to find the electric field at 1, 1, negative 1, okay, due to these three charge distributions. So we have got the answer for E1 and E2. Now we are going to find the answer of E3, okay? So let's look at the informations that we have. So now we have the line x equals to 0 and z equals to 2. Okay, so this one is the locations of the line. So if you draw it in 3D, okay, you draw in 3D, x equals to 0 is this point, and z equals to 2 is over here, right? So this one is the positions. Okay, so now when you have to draw the line, okay, you have to draw in this way. So the line will be something like this. It's a line, it's a red line. Okay, so this red line is infinite, yeah, it's infinite. The length is infinite. So meaning that it is approach to positive from negative infinity to positive infinity, and you have to find the electric field at the position 1, 1, 0. 1, 1, negative 1. Right, so 1, 1, negative 1, maybe the 1 is here and the 1 is here. So when you intercept them, you will get a point, and then negative 1 you move down. Okay, so this one will be the coordinate P that you want to look for is electric field. Okay, you want to know what is electric field. Okay, so let's use the equations, okay, that we have talked about before. Okay, this is the equations. So you have the rho L, okay, this is the line charge density, divide with the 2 pi epsilon naught, and you have the R, and this is the unit vector R. Okay, so basically, okay, this information has been given by the questions. The rho L is the 10 pi nanocoulombs per meters, right? So your only task here is to find the distance and also the unit vector R. Okay, so in order to find the unit vector R, the first thing is you must find the R, right? Okay, so R is the distance over here between the observation point and also the point T. Okay, if you remember, you take the observation point. You take the observation point minus the point T. Okay, so now it comes the task to find what is coordinate T. Okay, so coordinate T will be a point that is located along this line. Okay, so point T will be one of the points that is along this line. Okay, and this point T, okay, if you join it with the point P, you will get a angle 90 degrees, okay, with the line. Okay, so this line, okay, we know that is x is 0 because it's mentioned by the questions, and then the y you have no idea, and the z equals to 2, right? Okay, so you need to find out what is the value of y. So in terms of value of y, you have to refer to the value y of your observation point, which is 1. So in other words, the coordinate of your point T will be 0, 1 and 2. Okay, so now you are going to use it here to find the R. Okay, so here we do it straightforward. So this one is a 10 pi nano over 2 pi epsilon naught. Alright, and then you can find the R. So the R will be, observation point is a 1, 1, negative 1, minus 0, 0, 1, 2. Okay? Okay, so this one will be your calculations. So here you will get 1, 1, 2, 0. 1, 0, negative 3. Okay, so 9 plus 1, you have a square root 10. Okay, and this is square root 10. Okay, so you can fill up here square root 10. Okay, so you can start calculate this thing. Okay, you can start calculate this one. So let's calculate 10 pi times negative 9, and then going down you have a 2 pi constant, and then multiply with the 10. So you have a 56.47. 56.47. Okay, 1, 0, negative 3. Okay, so you will have 56.47. Okay, 0, and this one you can multiply 3. You get negative 169.4. Alright, so this one will be your answer for the electric field. Okay, observed at a coordinate 1, 1, negative 1, that is from the infinite line. Right? Alright, so now let's continue our lectures. So this one will be our week 3 lecture. Okay, let us try to refresh back what we have learned earlier. Okay, you have learned about charges. Am I right? So the charges could be positive charge, and the charges can be negative charge. Okay, so force exists between the charges. Is either it is attractive. For example, if you have a positive charge and negative charge, so the force in between them, okay, might be attractive. And if you have charges that has the same polarities, okay, so the forces between them could be repulsive. Okay, could be repulsive. So the reason why, okay, there is force between the charges is because there is an electric field, okay, between the charge. Okay, electric field between the charge. So for a positive charge, okay, so the electric field will be in the outward direction, right? And if you place it close to the negative charge, so it will terminate at the negative charge. So for the other directions, it will be going out like that. All right. While for the negative charge, okay, the direction will be inward. Okay, the direction will be inward. So this is what you have learned in the first week and also second week. So now imagine I take a charge here. Simply a charge can be positive and negative, and we already know it. There will be electric field surround it. Okay, so for the positive charge, the electric field will be outward, right? So now if I put this charge inside, okay, a spherical enclosure, okay, this is a spherical enclosure, okay, means like it's like a box, okay, spherical box. I put the charge inside this spherical box. Okay, so the electric flux, okay, the electric flux that pass through the box could be represented by a symbol or C. Okay, how to pronounce this one? This one is pronounced as C. Okay, so all the lines here, okay, all the lines over here, okay, they are electric field. And this electric field, they are actually represented by the flux line. We call this one as a flux line. Okay, so when I put this charge inside a spherical enclosure, the flux, okay, that coming out from the enclosure or pass through the enclosure, we call it as a electric flux. Okay, this is a C. Okay, this is the electric flux. Okay, so the value of the electric flux will be the same value as the value of the Q. Okay, so meaning that, okay, the unit will be equals to C coulombs, right? So now if I just focus on one unit surface, this is a small unit surface, small area of the spherical enclosure. If I want to talk about the flux, the electric flux coming out from just one small unit of surface, I will use the other parameter to represent it, which is the D. Okay, so D is the electric flux density, and the unit is coulomb per meter square. Okay, so now maybe you'll be a bit confused. So in this case, you have learned about two new parameters. One is the electric flux. All right, the other is this D, electric flux density. Okay, you need to understand these two things, okay, because they will be the fundamental of the Gauss law later. Okay, so we go back to this D and also the C, okay, this one. Okay, so this also means that, okay, this one will be equals to D multiplied with the area that you have, right? Okay, because this is telling you, okay, the density, okay, across a small section of surface. Okay, and if you multiply with the surface, you will be able to know what is the total electric flux, okay, coming up from the surface. So we could transform these equations again to this. Okay, so this concept is a little bit similar to the concept of integrations that we used before when we want to find the Q from the line charge. Okay, you will do this thing, right? if you want to find the Q from the surface charge, then you will do this thing, right? And if you want to find the Q from the volume charge density, then you will do this thing. Okay, so this one is quite similar to the cases of finding the Q. You use the integration to find the electric flux that is coming up from the surface. So now let's imagine this thing. We look at this thing first, all right? So D is the vectors. The dx is also the vector. So it is the dot product. Okay, it is a dot product between two vectors. So we have learned these dot product operations last semester in our multivariable calculus. Let's try to refresh back. You have had one vector A and one vector B. And if you want to perform the dot product between terms, you will be taking the magnitude of A, okay, multiply the magnitude of B, and then you multiply the cos theta. Okay, cos theta, the theta is the angle between the A and B. Okay, so if you apply this one over here, this one would be equals to, you take the D, okay, and then the dx, and then you multiply the cos theta, the angles between them. Okay, so the things that is actually telling you whether the flux is maximum or minimum would be this one, okay? The angles. Okay, if you look at the graph of a cos waveform, this is the cos waveform, right? So the angle over here is 0, right? Here is 2 pi, right? So over here would be, this one will be pi. Am I right? Okay, so you will get maximum of flux when you are at the positions of 0 degree. And also, this one is what? 3 pi over 2. Right? Okay? Get these things. So, we look at the surface. For example, if you have a surface over here, and the flux coming out from the surface is in these directions. Okay? So, the directions of your flux is this one. And your ds, this one is your ds, the ds. And the surface also facing in these directions. Okay, same directions. When you have two vectors that is facing the same directions, meaning that the angles between them is equals to 0. Okay, when the angle is equals to 0, okay, then you will get maximum value for these portions. 1. But okay, when your flux is in this direction, for example, this is the other case. If your flux is in these directions, okay, horizontal directions, okay, and your surface is in these directions, you have an angle difference of 90. If you put 90 over here, then it will be 0. This one will be this one will be pi over 2. This one will be pi over 2. This one will be pi, right? Okay. So when it is pi over 2, okay, the value will be 0. The value will be 0. Okay, the cos theta will be 0. So the whole term will become 0. Okay, when it becomes 0, it means that the flux now is become 0. Okay, telling you that there is nothing come out from the surface. Okay, nothing's come out from the surface. So if you want to have flux coming out from the surface, the angles, okay, between the D and also the dx must be 0. okay, must be 0. So this is the concept of for us to calculate the flux, okay, coming out from the surface. We look at one example. Is just imagine now you have a charge, okay, and then you pull it inside the enclosure, a spherical enclosures, and just now I already told you the total flux will be equals to the D multiplied with the surface area. So this also means that the D will be equals to flux divided with the area. Okay, so if this one is a spherical, this one is a sphere, if this one is a sphere, okay, so meaning that the flux will be divided with the area of the sphere. So the area of a sphere is equals to 4 pi r square. So you're taking this 4 pi r square, you put here. Right? So now you get the equation for your D. Okay? And this Q, okay, if you remember, I talked earlier before, this C, this electric flux is equals to the Q. So you could rewrite these equations, okay, to be Q divide 4 pi r square, the D. So taking these equations and compare it with the equation of the E that we have, right, this is the equation of the E. Okay, I didn't put the direction. You can put the directions. Okay, you can put the directions. If you put the directions, it will be R. Why is the R directions? You just look at the flux surround the charge. Okay, they will be in the outward directions. Outward directions. So this direction is the R directions. Okay, it's the R directions. Okay. So if you compare this thing, the difference lies on this one. Am I right? Here don't have the epsilon naught. Okay, so we can state the relationship between the D and also the E. Okay, the D equals to epsilon naught multiply with the E. So if you're able to find the F, you will be able to find the E. Now if you're able to find the E, you will be able to find the D. Okay, that is the electric flux density, okay, across the surface. Okay, we look at one example in the PowerPoint slide. Okay, in the PowerPoint slide, that is the example 14. Okay, example 14. Oops, not here. Okay, look at example 14. Right. Where is the example 14? Yeah, this one. Okay. So determine, okay, the D. Okay, the D. D is the electric flux density at the position 403 if there is a point charge negative 5 pi millicoulomb at this position and a line charge at the other positions. You have to find the D. Okay, so all the while, okay, what you have learned previously is to find the E, right? But now you have find the relationship between the D and also the E. So meaning that you can also find the D. Right? That is the electric flux density. Okay, so let me write down the important information from this example 14 in your PowerPoint slide. So your observation point, I will write it as a P, is the 403. You have a point charge. Okay, and its value is negative 5 pi millicoulomb. coulombs, and the position is 400. And line charge, okay, line charge, okay, this one is an infinite line. So the rho L given is the 3 pi millicoulombs along the y-axis. The y-axis. Okay, so we try to put them in the coordinate system. Okay. So first of all, you have a line charge along the y-axis. So maybe I can put here. Right, this is along the y-axis, infinite line. Okay, then you have a point charge at 400. Okay. 400 here is a negative charge. Okay, your observation point is 403. So somewhere here. This is the point P. 403. Okay, so now you have two sources of charge. One is the point charge, the other is the line charge. Okay, you have to find the D. Okay, and you know the D could be related with this one. Okay, so the concept of finding a D will be the same as the concept you want to find the E. Okay, so let's look at the equation you have to use. Okay, if you get it from the E first, let's see if I find the D from the E. So here you have to, if you have to find the total E, it will be E1 plus E2. Okay, so that is the E from the, or maybe I label it here, E from the Q and E from the line. Okay, so the E from the Q, okay, you can calculate by this one. Right, and for the E from the line, you could use this formula. Right, is 2 pi epsilon naught R and R. Okay, so let's start to look for the answer for this one. So for the Q, the value is negative 5 pi milli. Okay, divide 4 pi epsilon naught. Okay, so here you take in the observation point, that is 403 minus, okay, 400. Okay, so we go to the Q first, okay, the electric field from the charge first. Okay, so this one will give you negative 5 pi milli over this one. Then you will have 0, 0, 3. Okay, so meaning that the value is also 3. And over here you have 9, right? Okay, so you can start calculate this one. And for the line charge, okay, for the line charge, okay, the rho L is equals to 3 pi milli. Okay, so 2 2 pi epsilon naught r. Okay, so the r would be the deduction between the p and also the point t, right? So where is the point t in this case? So point t, okay, will have the x value equals to 0. The z value is also equals to 0. Okay, so you don't know what is the y value. Okay, so refer to the y of observation point. Okay, so means that this is 0, so this one will be also equals to 0. 0, 0, 0. So it would be 403 minus 0, 0, 0. Okay, so let's, okay, so you get so you have 5, huh? So it is 5 here, and this is also 5, right? Okay, so this one will be a total E, yeah? Now, the D equals to epsilon naught multiplied with the E. Okay, so you take the whole terms over here, multiply with the epsilon naught. Am I right? Okay, so you will get your D, which is equals to the same thing, over 4 pi. Okay, but the epsilon naught missing. Right. Okay, missing. This one, it will be 3. Missing. Huh? Right, missing. This one is missing already. Okay, the epsilon not missing already because you multiply over here. Okay, so your total D will be, okay, now you try to find out what is your total D. So negative 5 pi times 46.3 micro. Okay, and plus this one can cancel. Huh? Alright. So this one you have 60 micro. Okay, so the total will be, now you have to the X will be 240 micro. This is the X. Then you don't have the Y components, and you have the Z components. Micro coulombs per meter. Okay, coulombs per middle square. So this one will be your answer. Don't need the micro because I put the micro outside. Okay, so this is how you find the electric flux density at one positions using the formula. Okay, using the formulas.